Okay, something is happening. Everything good? Okay, I'll start then. Okay, welcome everyone. This is our third session, I think, in a seminar. Last time you heard about memory robustness from Giray, who did his PhD on that topic. He graduated last year. And we have another person who's doing a PhD on another topic, which is memory-centric computing, Geraldo. He's a senior PhD student in my group, most senior one. His defense is on April 29th. So if you're interested in learning more about what he has done, you can come to it, right? Yes. Okay, so Geraldo is going to talk about a fascinating research area, which is how to move the existing processor-centric systems to more processing in memory or memory-centric systems. Okay, you can take it over.
Thanks, Onur.
So let's see if everything's working. Okay. So hello, everyone. So as Onur introduced me, I'm Geraldo. I'm a PhD student here in the Safari Research Group. I'm graduating soon in April, and today I'm going to talk about one subject that I'm being conducting research since 2017, which are memory-centric architectures. This is a quite packed and dense summary of memory-centric computing systems. So I'm going to talk a lot, but if you want to interrupt me at any point, feel free to raise your hands or ask any questions about whatever I'm going to talk about next. So the main problem that we're trying to solve over here with memory-centric computer systems is that, as you probably have seen so far, if you use a computer, is that computers are often bottlenecked by data. And this happens for a myriad of reasons. One of the main reasons is that data is key for many application domains. So it's quite easy to highlight that today with generative AI. Probably you have already seen ChatGPT, the amount of data that is used to train and do inference over such large language models. But it's not only for AI. There are other key application domains, for example, genomics, where we have to store a lot of data and compute over that data to infer useful information from the computation that you are trying to do. And this is getting worse. So this is just an example for generative AI. Again, this is a talk from Grok. And then here in the x-axis, you have the memory footprint and then the y-axis, you have the training, the compute throughput of those models. And as you can see, since ChatGPT was released in 2017 until GPT-3, this is not even the most up-to-date data, the amount of data that was used to train those models or to the number of parameters that these models have stored have significantly increased in just 2 years. And it's projected to be even worse in the future. So basically, the more data that we can feed to these models, the better we can extract information out of them. But there is no limit over there, right? We can keep increasing the amount of data that you supply. So again, as I mentioned, this is a similar problem from genomics, where we store and we are trying to understand more and more complex information from the environment. We can combine different pieces of genomic data to try to infer, for example, potential diseases that might happen in a particular environment. So this is another example of a data-intensive task. So the main overview, I'm going to give some numbers later on for you guys to see how much this data-intensive problem impacts current systems, both in terms of performance and in terms of energy. And this happens because of the way that we're being designing systems so far. Later on, again, I'm going to introduce something that you might be familiar with, this von Neumann model, which breaks down the systems into 3 different aspects: computation, communication, and storage or memory. And we have been designing those 3 components in isolation. We have processor companies, we have memory companies, we have somehow some interconnect fabric companies. And this separation of interests have created specialization. And this means that like moving data around those specialized resources becomes more and more complicated. So this is what I was just mentioning for the von Neumann model. Again, we are the way that we design things or systems today is by separating communication, computing, and memory and storage in what we call a processor-centric manner. Processor-centric because if you look at the processor, everything goes around it. So this is just a design of an old multi-core processor, and the parts in red over here are the processor themselves, and everything around is designed to either move data or to store data for the processor to compute on top of it. Even though, as you can see, the majority of the silicon is not for computing itself. Yet we are bottlenecked by data. So this significantly impacts the performance of many applications. For example, this is a study from Google for their cloud applications, where they try to understand how much of their key applications that were running their servers were bottlenecked by data. And as you can see here, the majority of the cycles spent in some of those workloads are for data movement, not necessarily for computing. So in this example here, this is called top-down analysis. Only the green part is the computing, so you're doing something useful. Anything else is just either moving data or handling speculation. And again, from the end perspective, things get much, much worse than, because in terms of performance, we can try to hide this data this data movement latencies. But in terms of energy, there is no hiding. So there's no parallelism that you can avoid for data movement. And because we are designing things to be separate and connected via some sort of fabric, we have a part of the SoC or the system on chip that does the computation, and the other part that moves data. And moving data back and forth from one part to the other significantly wastes energy. So, for example, doing double precision computation, arithmetic multiplication, for example, versus reading data from your main memory takes, reading the data from main memory takes 2 to 3 orders of magnitude more energy than doing that complex multiplication inside your processor. And this is going to show up later on when you're talking about those processing memory architectures. This is just another view of the same idea, but for a different type of processor. And as you can see here, this is normalized to reading data from a file. As further away you move in the memory hierarchy, so register file versus, this pointer does not work very well, versus reading data from your cache to DRAM, the more and more energy you're going to spend moving the data inside the processor. Again, those numbers here might change depending on the processor organization that you're using and the technology, but the fact is that independent of them, if you are using a processor-centric approach, you are going to end up having orders of magnitude more energy expend on data movement versus computation themselves. So this is just another example to put some numbers in perspective. It's not only in big servers that this becomes a problem. In your laptop right now, this is a quite problematic approach. So we did this study in Google, and at the time you were looking at Chromebook laptops and key workloads that were running over there, like Google Chrome, for example. And we saw that for those workloads, the majority of the energy expend in those Chromebooks were for moving data back and forth from main memory to the processor. So the main reason that you're going to run out of battery soon is because of data movement. And this becomes even worse if you have specialized accelerators. This is another study that we did together with Google, where we analyze machine learning accelerators, the Google Edge TPU accelerator, for a myriad of different models. And we saw that for, depending the size of the model, the majority of the energy expend for that accelerator was, again, because of moving data back and forth or from the accelerator. This is just a graph from the particular work that I mentioned. I'm going to give more insights on that later on, but you can see, like, for LSTMs and transducers, at that time, this was in 2019, GPT was still not a very big thing. So that was the biggest model that they have for the Google Edge TPU at the time. And for those models, the majority of the energy here in yellow or moving the things around on the interconnects was because of data movement. So the fundamental problem that we're trying to tackle here is that we are performing or doing computation very far away where the data resides. So for us to fix this problem, we need to think about moving computation closer to the memory. So the closer that we are from the data, the less that you are going to move data around, the less that I need to expend that energy and latency and performance to bring data to my main processor. So we call this type of systems memory-centric computing systems, because they are fundamentally data-centric. I'm going to look at the data and I'm going to chase after the data, not the opposite. So if you look at the current processor-centric designs, so this is a picture of the Apple M1 architecture. As you can see, the majority of the real estate here is mostly for storing computation, and we are resuming ourselves or enabling us to do computation mostly in this part over here in the middle. So it's like a small percentage of the SoC itself. So if you break that abstraction and if you enable us to do computation distributed across this SoC, we have way more opportunities to reduce such data movement bottlenecks. So what we want in the very end is to treat memory not only as a means to store data, but we also want to treat memory as accelerator. I want to take my DRAM, for example, and tell my DRAM query some particular data that is in this database without moving the data from the processor. Or, as I'm going to show later on, I want to tell my DRAM, copy one array to another array. Don't bring any data to the processor, do it by yourself, because the data is already there. So why bring the data to the caches? For us to do that, we need to think differently on how we are designing systems. So to enable that is not just putting some CPUs nearby my DRAM. I need to think about how I'm going to express this computation from the application down to the hardware itself. So we need to revisit the computer architecture stack so that we can efficiently enable those compute memory resources. So this idea is not new, this idea of doing computation near where the data resides. The first work that we know that proposed something closer to this, let's call it intelligent memory, is from the 70s. There are two seminal works, and there were kind of phases of processing memory going back and forth. So this was initially proposed in the 70s, then it kind of died out because we could still design processors that were fast enough to mitigate these data movement problems. Then it came back in the 90s. Again, it faded out after some time. And then it came back again in 2010s and 2020s. And now we are seeing real products hitting the market with such ideas. And we are going to see an example of them later on in this talk. So why we should do a memory-centric computing today versus in the 70s or in the 90s? Because we are having a huge push from application. As I'm going to show later on for the accelerators that are available in the market today that follow this approach, you're going to see that they are mostly accelerators for machine learning. So for generative AI, for example, or for recommendation systems, there are quite large systems. There is also a push from technology. We are having problems scaling storage and memory further because of problems, as you saw last week, as that technology scaling causes like RowHammer. So that is in the middle, you as a designer get stuck into your application asking for more memory and you not being able to provide that amount of memory because of technology issues. So this gives a summary of the motivation of why we should design smart or processing in memory. I don't know if there is any question related to that. If not, we are going to start digging exactly on what those architectures are. So processing memory is a broader term for memory-centric computing systems. If you go to the literature, and during this semester, you might review several papers related to processing memory, and you might read about different terminologies. You might read about near data processing, computing memory, but all refers to the same idea of processing where the data resides. We further break down these processing memory architectures into two different types. Processing near memory and processing using memory depending on how those technologies are enabling computation. This is just a pictorial example. So these processing near memory architectures, we are going to think about them similar how we think about regular processors today. So you're going to still have memory and you're going to have compute, we might design them together, but we can also design them separately. But different from what you have in your laptop, instead of centralize the computing in a single place, we are going to start moving this compute closer and closer to the memory themselves. So either inside the DIMM of your DRAM, or inside the DRAM bank, or in this example here, for these 3D stack memory technologies, in the logic layer of these 3D stack memories. A different approach is what we call processing using memory. And this is a completely different paradigm. So here we are not going to think about logic and memory in two different aspects. We are going to use the operating principles of memory cells or memory circuitry to perform computation. So here there is no separation of what is logic and what's compute. The same array of memory sometimes can operate to store your data and sometimes to do computation. So this is going to enable some other type of processing memory architectures. As we are going to see later on, of those two different ways of doing processing memory leads to different trade-offs on complexity or efficiency for different application domains. But we are going to get there later on. So today, as I mentioned, the landscape for processing in memory, both in and using and near memory processing architecture is quite broad. At the time that I started my PhD in 2017, this was much different because processing memory was still quite a futuristic idea, or things that was just few prototypes that were being designed inside companies. But today we actually have processing memory architectures available commercially, so you can buy those chips and use those chips. And there is more and more interest on developing and designing those processing in memory architectures. Side story. At the time that I started my PhD, I never expected to see job opens that list specifically, oh, you are going to design processing memory for big companies like AMD that design processors, or server companies. But I'm looking for jobs recently, and then I'm seeing some posts that actually particularly specify memory-centric computing or processing memory architecture designs as one of the aspects of or roles for that job. So just this to highlight that what I'm talking here is nothing futuristic anymore. It's real and is available in the market, and it's going to be further available moving forward. So we are going to start simple. We are going to start with processing near memory architectures. We call those the architectures where we are going to design the logic and put those logic nearby the memory arrays themselves. But this is not magic. I cannot design whatever logic and put closer to whatever memory without taking into considerations the design challenge that imposes for you as a designer. So there are many design challenges. I'm going to highlight at least 3 over here. The first one is the limit power and area budget when you're trying to design processing or near memory architectures. So you have I don't know if you have already seen a real DRAM DIMM, for example, that is a form factor, right? Is relatively small. So if you want to put a processor over there or a GPU or something else, you need to take into consideration that you might not want to increase the area and power budget of that particular device. And this is one particular problem, especially for memory devices that are optimized for capacity per bit. So you as a memory manufacturer wants to make most of your revenue from storing the data in that particular device. And if whatever logic that you're adding that, of course, can bring a different type of revenue, but it's logic that either is extra or you are removing capacity for your memory technology. And we are going to see example of those over here. So there is a trade-off over there on the space that you're occupying for computing versus the type of computation itself that you can end up doing. On top of that, there is power, right? How you dissipate that power that is generated by computing. So computing is not free. And that brings me to the second design problem is that this power that's dissipated is usually dissipated in terms of heat. So how are you going to remove the heat from your silicon, right? So how are you going to handle thermal constraints for your design? So again, if you have opened up your process, not necessarily your laptop, but the desktop, there is usually a fan over there, right, on top of the processor, because that processor generating hits which can harm the circuitry. If you have now compute in your DRAM, how you're going to dissipate that particular heat that is coming from the compute from your storage or your DRAM media itself, right? Usually DRAM handles thermal dissipations in a passive way, so you don't put a heat sink on top of the chip. And the question is, do you want to put a heat sink on top of your chip? That overcomplicates and adds extra costs to the device itself. This becomes even more complicated when you look at 3D integration, because in 2D, okay, it's a planar way, I can maybe put a heatsink on top of it. But what if I'm designing a 3D stack manner? So I have many layers, some layers of DRAM, some layers of compute, and I need to dissipate that, that heat that is being generated by one of those layers out to not harm the circuitry, right? How I handle that. And there are solutions and there is research related to that. The third challenge is how can I manufacture logic plus DRAM? So there is a way, there is a reason why we have processor companies designing processors and memory companies designing memory. Usually those manufacturing fabrics leads to different trade-offs. So your processor design is heavily optimized to speeds. So you want to make your clock as fast as possible so you can extract performance, while your memory is optimized for cost per bit. So you want to store as much data as possible and costing the fewer amount of dollars or Swiss francs. There is this problem that if you try to manufacture logic using memory, the memory manufacturing process, you're going to end up with a processor that is slower than a processor manufactured using a processor manufacturing process. And if you do the opposite, if you try to manufacture memory using logic process, particularly DRAM, you're going to end up with a circuit that is not optimized anymore for capacity. So that's going to take more area and hence more cost per bit. So those are different trade-offs. We are going to see how this impacts real products when I talk about real process near memory architectures. You're going to see that the cores over there tend to run at lower clock frequency that you might see in your processor here. And this is because of these difficulties of manufacturing processor using memory manufacturing process. Okay. Usually when you're trying to design those processor near memory systems, you as a designer should take into consideration those limitations. And in these works that I'm going to mention later on, or the works that we've been conducting here in Safari, we are trying to take those into consideration. So those are some works that I'm going to mention later on that take those design challenges into considerations. Okay, so you have your application domain that you want to accelerate because it suffers from data movement problems. You have your constraints in mind when you are trying to design logic plus main memory. So now what are your options to design your system? What type of model or designs you can add? So as I mentioned earlier, designing processor near memory architectures is not much different than designing your regular SoCs. So the options are quite similar, but the trade-offs are different. So for example, you can have general purpose programmable units inside the memory. And usually they are going to show up in the literature as very simple WIMP cores, in other cores or RISC-like cores that can be used to accelerate different workloads. I'm going to show two examples here from academia, one from academia for graph processing and another one from industry for that is a startup company from France that designs those general purpose programmable cores. Another option is designing fixed function unit accelerators. So let's say that you have a kernel that is generating memory bottlenecks for your system. That kernel performs a single operation most of the time. Think about, again, generative AI. The main kernel there is either a general matrix vector multiplication or a general matrix multiplication. So you can design a unit that only does that, only either does matrix to vector multiplication or matrix to matrix multiplication. Usually, those type of designs are more efficient because you can use the silicon space that you have available just for that particular task. But then again, you are bounded by that particular computation for your design. Again, I'm going to show later on one example from academia that does so, and another example from industry. And finally, you can have some type of reconfigurable logic nearby the memory. And here, usually you can either think about memory devices that are capable of doing something like FPGA-based computing, or a more coarse-grained type of reconfigurability using CGRAs. And again, I'm going to show examples from both industry and academia over here. So all of those have different trade-offs. So the first one, the general purpose cores give you more flexibility in the design at the expense of not being optimized for a particular kernel, while the fixed functional units give you that optimization, but limits your applicability to a particular application domain. And the configurable architectures sit somehow in the middle. Okay, so let's look at the examples for those processing near memory designs, starting with general purpose programmable cores from academia. And this is one of the examples that we did in Safari. It might be one of the available readings during the semester, where we took graph processing workloads and tried to accelerate them using general purpose processing near memory cores. Usually graph processing workloads are quite irregular, so they do a lot of irregular memory access, and they necessarily are very computing demanding. So this is an example here of one particular application. This is PageRank. PageRank is an algorithm that is used for sorting web pages, famously used by Google. And in this PageRank algorithm, what you basically do is a multiplication and addition of weights in a very large graph in the internet, right? So you keep accessing pages that have, or nodes that have similarities with each other, and updating those values, and those pages might be random, so there is a irregular memory access, but the amount of computation that you're doing per node is fairly simple. It's a multiplication and addition. So we are going to use this, at the time, newish memory technology called 3D stack memories, where we have layers of memory, layers of DRAM, stacked together in a basic die. And this basic die is capable of being not necessarily capable of computation, but you can embed computation over there because those are manufactured in a different manufacturing process. So this particular architecture here that I mentioned is like hybrid memory cube, does not exist anymore, it was discontinued, but you might have seen around, if you're buying GPUs, something similar called hybrid HBM, which is a fairly similar architecture than this one, which is again organized using 3D stack layers of DRAM connected to a basic die that is capable of doing some sort of computation, or can enable some computation over there. So we are going to use this 3D stack memory architecture to add some simple in-order cores in the logic die, so that I can offload that PageRank computation over there. And since we have many nodes in a graph, and this graph can grow a lot, we are going to have some sort of interconnect or some sort of topology of many of those 3D stack architectures, so that we can scale out the system to a very large graph. And even though you are designing a system for graph processing, what we embedded in the logic die is basically some simple wimpy in-order cores that can be used to accelerate something else. So it's not necessarily fixed for graph processing. And this is just some results of using this architecture versus using the same architecture, for example, with high bandwidth memory chips. And we can see that you can significantly improve performance because you are not, or we are mitigating such data movement bottlenecks that those graph applications would suffer from using those 3D stack architectures plus processing memory. This is the same architecture, and we can see here that you can also significantly reduce energy consumption. So this is the Tesseract paper. The list of papers I think is not available yet for this semester, but it might be one of the papers that you might read or follow-ups of Tesseract. Okay, that is an example of general purpose processing near memory cores from academia, and now example of processing near memory cores from industry.
So if I understood it correctly, you have like multiple cores.
Yes.
And they have sometimes different instruction sets.
The instruction set is the same, but they can execute different instructions. So those are think about this as a distributed system. We have many cores across the network of those 3D stack memories. So they are all working in the same graph problem, but they are the same. They have the same instruction set architecture, but they can do different computation. Any other question? Okay, if not, let's look at the industry version. So this is a little bit different from the Tesseract architecture that I just mentioned, because here you're not going to use 3D stack memory. You're going to use regular DIMM devices, but you're going to embed some programmable cores inside each one of those DRAM chips to do some general purpose computation. So this is architecture that you can go and buy. Of course, you're not going to find a Digitech or something. You need to enter in contact with the company. Again, it's a French startup, but they have servers that have those processing near memory architectures, and then you can rent time over there, or you can buy the chips from them themselves. And those are standard DIMM models with some embedded general purpose chips on them. So the way that this works, this is not necessarily for you to replace your main memory with those chips. You are going to extend your system with those memory chips. And you're going to think about this similar to how you think about a GPU, where you're going to use those particular memory models to as accelerator for a particular data-intensive task. So basically, this is like is what's called a loosely coupled accelerator, where you have a particular application that you have interest in accelerating, and the whole CPU at some point offloads the computation to this processing memory cores. This is some details, and again, as I mentioned, this resembles the same way as you do GPU-based computing. So this is just a picture of their system organization from the patent that they initially released for those architectures. So as you can see here, we have your regular SoC, so your regular CPU, and then you have those specialized DRAM models. And inside those specialized DRAM models, you have your regular DRAM array, which stores your data, but different from the DRAM arrays that you have in your laptops, you also have some programmable cores that can be used to do some computation. So this is just another view of the same system organization. As I mentioned, you have both your regular main memory and this process memory enable memory. And inside those chips, what we have is those PIM chips, where each chip has some, in this case here, this particular organization, 864 megabytes of DRAM memory and 8 DRAM processing units called DPUs. So in total, in a single rank, you have 64 of those, and then you can scale up the system to 2,500 something of those DRAM processing units. I'm going to give more details on the design of these units later on, but this is just a view of the system, how it looks like. You have your regular CPU, you have your regular DRAM, and then you have equipped in the same motherboard those process memory enable DIMMs, which are going to be your accelerator. This is just some details on how this operates. So before you're doing some computation, you need to offload the data to from your host memory to your process memory enable memory, and once the computation is done, you can move the data back from the CPU, from the PIN enable memory to the host memory using different types of data transfers. You might think, oh, the whole idea that you're talking about so far is mitigating data movement bottlenecks, but you're making me move the data from this host memory to these specialized memory chips is in this increasing the memory data movement bottleneck. This is true. This is just one way of doing that. But the main idea here is that the amount of intermediate data that you produce when you're trying to do some particular computation is going to be larger than the amount of data of the input and output that you're generating. So this is similar to how you do GPU computing, right? So if you just have a small task that you need to offload the data to the GPU, compute something very small and move the data back, it's likely that the round trip latency is going to be larger than just doing on the CPU, which even though your CPU is much weaker than your GPU. But if you somehow can amortize that data movement, that initial input and output data movement copies, you can improve overall performance for your system. There are reasons why the UPMEM company is doing things like that. Doing a system like this, which we have loosely coupled accelerators, is somehow easier. It's not necessarily easy, but it's easier than as if you completely replace your main memory with those processing memory models, because you need to change many aspects of your system. So you need to, because your main memory is just not a passive element anymore, you need to handle things like data coherence, operating virtual memory, all of those things need to change, which are more drastic changes than just using an accelerator like that. So we expect that probably in other in future generations, you're going to improve on that over time. But I don't work for them, so it's not necessarily a work from the company. So this is just other details about that particular organization. These particular pin chips here inside this pin enable memory cannot communicate with each other. So if you are doing a collaborative computation inside those process memory cores, and you need to share data, they need to share this data via the host main memory, which again can create overheads for the overall computation. This is just again from their patents that they filed. Another view of inside the chip. As I mentioned, inside the chip we have those DRAM banks and then some pin cores, right? And those pin cores are simple here. So they are simple 14 stages pipeline multi-threaded cores that has a ISA similar to a RISC like ISA. It's not necessarily that, but fairly similar. And you can use, since it's a general purpose ISA, you can use that to accelerate many different applications. And we are going to see examples of applications being accelerated using this hardware later on in this talk. So this is just another view. An important aspect of this processor, as I mentioned earlier, right? If you're trying to manufacture logic using memory process manufacturing, you're going to end up running your hardware at lower clock frequencies. One of the reasons because of this challenge that I mentioned earlier on this incompatibility of logic plus memory manufacturing, right? So as you can see, the frequency that those cores run is quite small, so 400 something megahertz. As a contrast, I don't know, your computer probably run at something like 4 gigahertz at peak, or even some processor can run even faster. So it's not necessarily a really fast processor, but is a lot of them. So you can have, as I mentioned, 2,000 of those processors work in a single task, and that sheer parallelism, plus by the fact that you have access to faster access to memory, can lead to performance improvement for data-intensive applications. And as I mentioned earlier, those are multi-threaded and pipeline processors. Some details about the instruction set architecture. As I mentioned earlier, they are similar to a RISC like a 32-bit ISA. And if you want to learn more about those architectures, we have some lectures online related to them. I don't know necessarily if this paper is going to be one of the readings again, but in this paper here, we took this architecture and then we benchmarked the architecture to try to understand its bottlenecks and what we're trying to answer for what type of applications this particular architecture can be good for. And based on that, we create this benchmark suite that's called PRIM, which several workloads that stress this architecture in different ways. And you can use these workloads to study this real processing near memory architecture. And it's available online. So this is just more analysis on the UPMEM architecture. And as I mentioned earlier, this architecture can be used to accelerate a myriad of different applications. And we are being slowly porting different applications from very simple applications to more complex over the time as we further understand the programming model and the hardware itself. So for example, we did works where we offload classic machine learning training applications to those process memory chips. Here, think about something like, don't think about generative AI, think something like k-means, decision trees, linear regression, logistical regression. And we also propose optimizations for those architectures so that we can further improve performance. There are other workloads that we have offloaded to this architecture, like sparse matrix vector multiplication, trace addition functions, sequence alignment for genomics, homomorphic operations, reinforcement learning. These are fairly new ones for distributed training. So this is for distributed stochastic descended algorithms, usually for machine learning training. So all of those are available online, and some of those papers might be in your reading list. Okay, so this concludes the UPMEM architecture. Is there any question related to them? Okay, if not, let's look at the fixed functional units processing near memory architectures. So the main limitation, as I mentioned, this is not only for PIM, right? But it's also for general purpose computing versus fixed functional unit computing. If you can specialize your hardware, the more that you can specialize your hardware, the better performance or the that you can extract if you do the design correctly, of course. And this is particularly true for process memory because, as I mentioned, you have constraints related to area and power budgets, right? So if you can spend your silicon in important tasks that your application that you're going to offload is going to do, you can further improve performance. This is just an example for that Google work paper that I mentioned earlier, where we offload several tasks from those Chromebook devices to the PIM cores and to two different types of PIM engines, either general purpose ones or specialized fixed functional unit ones. And as you can see in this plot here, of course, if you specialize, you can further get performance improvements out of the system. So there is an incentive of specialization for processing memory. The way that you need to go after that specialization is by really understanding your application or what you want to offload. So this involves taking your application, profiling your application to try to understand what are the hardware software requirements, the performance and energy bottlenecks that application might suffer in your processor-centric design, and use that information to co-design your hardware and your software when you are doing the fixed functional unit accelerator. And as I mentioned, this usually can lead to high performance and energy efficient processing memory chips. We are going to show, this was the alarm. So I'm going to, before the break, very briefly, I'm going to show an example of academic work that we did for fixed functional unit based processing near memory. And this is the work that I mentioned where we use the Google Edge TPU accelerator to accelerate 24 different edge neural network inference models used by Google at the time. And we saw that those models, some of those models were memory bound. And we saw some insights from those works that if you take layers of neural networks from different models, you're going to see significant variation on the requirements for different layers. So different layers are going to have different data reuse metrics or different parameter footprints or MAC intensity. And this varies across models and also across layers inside the same model. So the idea here was, instead of designing one big monolithic accelerator like what Google was designing to accelerate different models and different layers inside those models, we can specialize. We can design smaller accelerators, some of them in the CPU, some of them inside the memory, and during the runtime, understand the properties of those layers and offload them to the appropriate accelerator. So this specialization further improve performance, reduce underutilization of a monolithic design, and improve overall efficiency. The question that you might have is, how many accelerators is enough to accelerate 24 different neural network models with myriad of different layers? And we saw that usually layers of neural network models cluster in two different classes. Some classes are more compute-centric layers. Those layers are layers that are heavily on multiply and accumulate operations and also have high data reuse. And some of their layers are more data-centric, and those layers are the ones that do not do many multiply and accumulate operations and have very large parameter footprints. So you need at least two different types of accelerators to accelerate those 24 different neural network models. There is also the question of the scheduler. So how can you identify during the execution for which layer, which accelerator goes? And to solve this issue, we created a software runtime scheduler that uses layer characteristics to, during the execution time, offload the layers to the appropriate accelerator. I'm not going to get into detail on the model. The important thing here is that by doing so, compared to the baseline Google HTTP accelerator, it can significantly reduce energy consumption because we are not using, we are using the data-centric accelerators to accelerate data bottleneck layers, so you don't move the data to the CPU. And this can also improve the throughput for inference for those models compared to the baseline HTTP accelerator. So this is the Mensa paper. And I think we are going to take a 5 minutes break and then we continue for the industrial solutions for fixed functional unit processing near memory architectures. Before there's any question related to Mensa? Okay, so let's come back at 5:10. That should be enough. Soccer, like the, I don't know, competition. So, these are new Zoom features. Okay, so let's get started again. Again, we are talking about fixed functional unit processing and near memory systems. Now I'm going to talk about industry-based solutions that follow these design principles. So in 2021, Samsung first announced those architectures called, at the time was called FIM-DRAM. It keeps changing name. It went from FIM-DRAM to HBM PIM, then to Aquabolt, and only God knows what it's called like right now. But again, those are prototypes from industry that are fixed functional unit processing memory architectures targeting to accelerate AI. And similar to what I mentioned for Tesseract, here Samsung are using 3D stack memories to do this acceleration or to enable this processing near memory solutions. But it's a little bit different from Tesseract. As I mentioned earlier, that is this trade-off, right? In terms of how much logic you put inside the chip versus the capacity of your memory device. And Samsung is basically playing this trade-off over here. So these HBM 3D stack memories that I mentioned earlier, usually they have in the second generation around 8 layers of memory. What Samsung did is instead of having 8 layers of memory, I'm going to have 4 layers of memory, and then I'm going to embed computation in 4 other layers so that I can do neural network inference inside the chip. The difference is that the capacity went from 8 giga, I think bytes or bits, I don't remember the number, I think it's bytes, 8 gigabytes to 6 gigabytes. So there was a cut on the capacity of the chip so that you can enable computation. So this is another trade-off that you have to take into account. The architecture of those chips for computing are, as I mentioned, basically some units to do multiply and accumulate operations. So here we have a multiplier, a fixed function unit, float point multiplier, and then adder, and then combined you can do operations like multiply and multiply add, which again is key for neural network inference. This is just the die picture of the architecture. One key thing here is that in this architecture, one of those MAC units is shared across 2 different neighboring DRAM banks inside a layer of the chip. So as I mentioned, this was the initial design from 2021, but Samsung keep working on those this architecture. So this is 2023. They released that same version of a new version of the same design targeting generative AI. And as you might know, the generative phase of generative AI, like GTP, is fairly memory bound. And the main operation that you do over there is general matrix vector multiplications. So they want to offload those GMV operations to the memory chip themselves. And they have 3 solutions to do that, depending on how you want to embed it, or what is your target system, basically. If you have your regular GPUs, they have a solution that equips that adds those HBM capable memory to AMD GPUs, and they use that to accelerate GPT-J. It's fairly small model at the time. This is just some marketing numbers. They see 2 times performance improvements compared to running the same inference workload just on the GPUs. If you have if you want to do inference on your phone, for example, usually we use low power memories. And again, they have a solution that embedded computation to those low power memory devices. Again, the architecture is very similar to what I mentioned before. It's some matrix vector multiplication engines that is shared across neighboring banks. But this time around, the architecture is not 3D. It's regular planar 2D low power DDR devices. And again, they show significant performance and energy gains when you're trying to run inference on your phone for those PIN-enabled systems. So if you don't have, if it's not like a regular GPU, or if you want to scale out your system for capacity-bound generative AI systems, what they use is this fairly new interconnect fabric called CXL. It's a consortium that standardizes this fabric to scale out systems. And basically, they added computation again, either at the controller of the fabric or inside the chips of the memory themselves. And again, they show some energy savings and throughput improvement for those particular systems. So there is a very product. Samsung was creating a product line out of this processor memory architectures for generative AI. And it's not Samsung. SK Hynix is another memory manufacturer from Korea. They have, again, a similar design. The main difference here is that the processing engines here are not shared across the banks. This is the organization. You can see that each bank has its own processing unit. But again, the computation is fairly similar. There's a multiply and a adder tree for accumulation. And since this is for neural network inference, they also have activation function here for sigmoid inside the processing element themselves. So those are examples from two main memory manufacturers, Samsung and SK Hynix, of those devices. So Micron also have something. The Micron is another memory manufacturer for that is based on the OS. They didn't disclose much, so I didn't include it over here. But they are also, at least I talked to them last time that I was in this conference in the Bay Area called FMS. They have one processing memory design, but was fairly obscure at the time what exactly it was. But they're also working on them. So this is just to highlight that the main memory manufacturers are also working on those processor memory solutions. Is there any question related to that? Okay. So finally, FPGA-based processor memory. So I'm going to give example here. One example from academia is what we did in Arrow for weather prediction, where we use these DDR-based FPGA boards to embed some computation over there. So the computation is already there, right, in the FPGA board. We just map the weather modeling software or application to the FPGA itself and offload it to the FPGA when you're trying to do the computation. And again, we can have some performance improvement compared to a baseline processor-centric systems. You also have examples from industry for similar architecture. So this is another architecture from Samsung. It's called XDIM from 2021. And here, the target is not necessarily generative AI. Is at the time was for recommendation systems. So this is just a picture of the organization. What they have is those this special FPGA boards here, or this special DIMM boards here, which inside that on top of the fan you're going to have a FPGA design. So this is the board, the card. You have two DRAM ranks, FPGA, which you can reconfigurable to do some particular computation. And what they are reconfigurable for, in this particular case, is for recommendation systems. But since this is reconfigurable, does not need to be recommendation systems, can be something else, like sparse length sum or database operations as well. So we have lectures on those that further explain those architectures. But this concludes the processing near memory part. Is there any question related to processing near memory? Okay. If not, we are going to shift gears a little bit to processing using memory. And recall that here, we are not going to add logic for computation. We are going to use the memory cells themselves to perform some sort of computation. But before I explain how this works, I need to give you a brief introduction to DRAM, which probably already have from last week. So I'm going to be fairly fast. I'm already fast anyway, but I'm going to be even faster on the organization over here. So as you might already know, DRAM chip is organized as a hierarchy of components. And the top of that hierarchy, we have what is called a DRAM mat. Those DRAM mats are to the array of DRAM cells, which are horizontally connected to a word line and vertically connected to a bit line. So bit line shares local system amplifiers, and word line shares a local road decoder. So in the next level of the hierarchy, what we have is DRAM subarray, which is a collection of multiple of those DRAM mats, which shares a global word line connected via a global row decoder and a global system amplifier, which is used to move data from the local system amplifier to the I/O interface and eventually to the memory subsystem. So for you to access DRAM, the memory controller issues two main operations. The first is row access or activate. This operation basically connects one row of DRAM cells to the local bit line, enabling the local bit line to be perturbated based on the voltage level stored in the DRAM cells themselves. The local system amplifier is activated and inserts this voltage perturbation level and amplify the data to either 1 or 0, depending on the data that's stored in the DRAM cells. After that, the data is latched in the local system amplifier, and the memory controller can issue read or write requests to that latched data, moving the portions of the data flow from the system amplifiers, local system amplifiers, to the global system amplifiers, and eventually to the memory channel. So this is a very brief overview of DRAM. And what we are going to start building computation based on this principle that I just mentioned extremely fast, starting with in-DRAM row copy. So let's say that I want to copy this white box inside the memory to the black box inside the memory here. And I don't want to involve the CPU. So I don't want to move cache line reads columns of data, move them to the memory hierarchy, to the cache hierarchy, to the CPU, and back and forth. I just want to tell my memory, copy the white box to the black box, and don't involve the CPU. So how can you do that? First, what are the benefits of doing that? Of course, it's low latency, does not utilize the memory channel, does not create cache pollution, and does not generate data movement, right? And by doing so, we can significantly improve performance and reduce energy compared to moving the data using a DMA engine, for example. So the way that this is going to work is fairly simple. And this mechanism is called row clone. So what we do is, first we activate the source row, exactly as I mentioned in the background. So this is just going to copy the local data to the row buffer. Then instead of sending a read command or a precharge command, I'm just going to activate the destination row. And when I activate the destination row, this connects the DRAM cells in the destination row to the row buffer, which has the data from A. Since I'm creating a path from that cells in row B to the row buffer that has the data of A, I'm basically copying the data from the row buffer to the DRAM cells in row B, hence doing this in DRAM row copy. And we can do that without very negligible hardware costs from the chip itself. And by doing so, we can significantly again reduce latency and improve latency and reduce energy consumption compared to using the CPU to do so. This was for copy. So let's say now that I want to do something else. I want to do and or operations. We are going to use the very similar idea, multiple row activations here, but now I'm not going to do one copy after the other, one activation after the other. I'm going to do 3 activations of 3 DRAM rows at the same time. When I do that, 3 activations of the 3 DRAM rows at the same time, the 3 DRAM cells that are connected to the local bit line are going to perturbate the local bit line at the same time. And since what we have in the local sense amplifiers is basically a differential circuit, this local sense amplifier is going to pull the voltage level to the majority of the voltage levels of the data stored in the 3 cells activated at the same time. So basically what we have here is a majority of 3 of the cells involved during the operation. So here before we have 2 rows in blue, 1 or 2 rows that have charge data and 1 row with discharge. And when you do the majority of that, that is charge, right? So, or blue if you want to abstract it away. And by controlling one of those inputs, I can either do a OR operation if one of the rows stores 1, or AND operation if one of the rows stores 0. So now I can also do Boolean AND and OR over the data stored in the DRAM chip itself. And by doing so, we can accelerate some applications that uses book bitwise operations like databases compared to using the CPU. And this is the work that we did in Ambit. So, okay, we can do inside the DRAM without involving the CPU and without including logic. We can do in DRAM row copy and by doing consecutive activations, or in DRAM and the NOR operations by doing triple row activations. What about more complex operations? What about additions, subtractions, multiplications, which are actually used in application? We can compose those more complex operations using either in DRAM row copy or in DRAM majority. And this is what I did in this work called SimDRAM, which is a framework that basically takes as input a desired operation, expressed using AND and OR gates, converts this sequence of operations to majority-based computation, because as I mentioned earlier, what basically the DRAM is doing is a majority of 3 operation. So let's express the computation based on that majority of 3, and then converts that majority not graph into a sequence of either in DRAM row copies, sequence of activations, or in DRAM majority, so triple row activations in what we call a microprogram, which is a recipe that tells the DRAM how to do that computation. Also, we have a control unit in the memory controller that when the application wants to offload some particular computation, let's say in DRAM add operation to the memory chip, this can be done transparently from the user. So this all sounds quite abstract. I'm going to try to illustrate it a little bit more in this example over here. So let's say that we have 2 arrays, array A and array B. Those arrays have as many elements as columns in my DRAM subarray, and each element in this array is 1 bit. And A, all of the elements store 1, and in B, all of the elements store 1 as well. And I have this carry in row here that's just pre-initialized with 0. So basically, I want to add 1 and 1, and I want to get 2. So how you do that? So the first step is taking an adder. So this is just a RIP carry adder, and we are going to convert this RIP carry adder using AND OR and XOR gates to its representation using only majority gates. Why again? Because what you are doing when you're doing triple activations is majority of 3. Then I just need to traverse this graph here, node by node, and issuing triple activations to do my operation in the DRAM chip itself. So I go to the first node here, which involves activating rows A, B, and carry in at the same time. I send this activate those 3 rows. The majority of blue, and yellow, 1, 1, and 0 is 1. And I store that data in a carry out row. Then I move to the next gate, which involves activating carry in A and B bar, so a negated version of A. And that means activating doing a majority of 0, 1, and 0, which is 0, and I store this data in a temporary row. Finally, I go to the final majority gates, which involves activating the 2 previous computed rows and input a row A, and this is going to be 1, the majority of 1, 0, and 0, which again is 0. So in the end, I have in the sum row a lot of zeros, and then I have in the carry out row a lot of 1s. And then I can represent that. This is 1, 0, this is 2. So I have my in DRAM addition operation. And I can do this to whatever computation that I can express in and using Boolean gates. So I can do the same thing for addition, for subtraction, for multiplication, to division, as wanted. Another interesting thing is that if you're operating your DRAM chip, as I mentioned here, basically what we have is a very wide. So you have as many operands as columns in the DRAM array, and you have at least 65,000 columns inside a DRAM subarray in DDR4 chips. Bit 0 engine. Bit 0 because, as you might have noticed here, I'm going bit by bit. So if I had, if those elements here was, instead of 1 bit, was 2 bits and as many operands as DRAM columns, I would have to repeat the same process twice. If it was 3 bits, 3 times, it was 4 bits, so on and so forth, as many bits as I have. So this is, in the end, we are creating a very wide bit zero SIMD engine using DRAM cells now for computation. And note that there is no logic added. So I didn't have to add anything. I just activating rows inside the DRAM chip. So as in this work, we use this framework to implement 16 complex operations and use these operations to accelerate 7 common real-world applications, and we see significant performance and energy improvements compared to running the same operations inside the processor. Okay, it's all nice, but is this efficient? The answer is not. So what happens if you don't have enough data to fit inside all of those 65,000 columns, right? And 65,000 is a lot, actually. So very rarely, how many times you have you write a loop which operates over 65,000 elements every single time? It needs to be multiples of that. Otherwise, you're going to end up in this situation where portions of your row have data that you're going to operate over, and portions of your row does not have any data that you're going to operate over. Since when you do the activation you do per the entire row, you're going to end up activating portions of the row that does not have useful data, which causes throughput and energy loss. The idea to solve this is a fairly old idea related in DRAM organization, which is called fine-grained DRAM activation, which we are going to segment this global word line here that spans across the multiple DRAM mets inside the DRAM subarray, so that I can activate portions of the DRAM row as needed for the processing using DRAM operation. So basically, we do that. We segment the global word line, and now if I want to do processing using DRAM operations only in half of my DRAM columns, I can only activate those particular set of DRAM rows. So hence, we can improve utilization. Another thing that this enables is that if I'm using only half of my subarray to do a computation, and I have data-independent operations in my queue, I can use the other half to do other computation that is not related to the previous activated one. So now I can have 2 different instructions. Think about, for example, addition in the blue part, and then a subtraction or a multiplication in the orange part, executing together inside the same DRAM subarray in a multiple structure, multiple data execution model. This is why it's called MIM-DRAM. It's from MIMD. And the SIM-DRAM that I mentioned before was because of that was a SIMD mode, SIMD engine. Another thing that this enables is that in the background, I saw that there is this global simplifier, right, which is connected through the many DRAM subarrays, DRAM mets in a subarray. So I can use that to move data around those different DRAM mets, which enable me to do computation like reduction operations. A third thing that this enables is that, surprisingly or by coincidence, the number of DRAM columns that you have inside the DRAM met is around 512, which is the number of SIMD lanes that you have in vector processors in your CPU, like AVX 512. So I can map those vector instructions to process using DRAM instructions transparently from the user. So I don't need to program this manually anymore. And we implement this compiler support that basically auto-vectorize your loops to generate those vector instructions, then schedule the computation across the many DRAM mets inside the DRAM subarray, and finally generate the binary that you can run in the architecture itself. And by doing so, we can accelerate many applications. Those are 12 different applications from 4 benchmark suites. And you can see that it can significantly outperform GPUs and prior process using DRAM architectures. So this is all have been done in simulation, so in using theoretical model or analytical models, but we see that commodity off-the-shelf chips, the ones that you are using in your computer, not necessarily the one that you're using computer, but fairly similar, are very capable of doing this sort of processing using DRAM computation. And you use these FPGA-based frameworks to show that, I want to get here, that commodity off-the-shelf DRAM chips by violating the DRAM timing parameters of community of the shell DRAM chips, are already capable of doing in-DRAM row copy, in-DRAM NOT operations, and 6-input AND, NAND, or NOR operations. By doing basically what I mentioned before, multiple row activations. So the way that you do it in commodity of the shelf DRAM chips is a bit different from the theoretical model, because I cannot activate 3 DRAM rows at the same time, the memory on the regular devices. So what I do basically is, if this slide is not here, is violates the timing between 2 back-to-back activations. So when I do that, I can realize different operations, as for example, a NOT operation or NAND and NOR operation over here. So NOR operation. So and we have in our FPGA infrastructure, I label us to do this memory timing violation. So you're not going to be able to do this in your CPU right now, because you already have a memory controller that is configured, and this is like illegal operation. But if you take your DRAM chips that actually buy from Digitech and place on these FPGA boards and do this activate pre-charge activate commands, you're going to be able to do these in-DRAM row copies or Boolean operations, of course, with some reliability margin when you're doing so. Is there any question related to this?
So this is all assuming that it's all destructive reads, right?
All of those are destructive reads, yes. So I'm going to show later on processing using memory for emerging memory technologies. But this is a bit different because over there you can design the array accordingly, so you can do the computation. Here we are not redesigning the chip. The chip is already designed. You're just operating differently. Okay, and this is the FPGA prototype that you have in your lab. If you go to ETZ, there is something similar to that in our cave. It's very warm there. And then we test different models for different memory manufacturers, and we do a bunch of studies to understand the reliability or the robustness of those operations and different effects that these operations have, for example, on temperature or data pattern for different computations. But that is what I want to highlight for this. Is quite exciting because this shows that we can use memory chips that are not designed for compute to do something else. So we are telling the memory manufacturers, use those chips. Don't just use these chips to store data. You can do way more with the chip that you already have, which can enable many things. And this very likely is one of the readings for your semester. Again, I don't know the list yet, but it's a fairly new paper, so probably can be one of the lists. So I mentioned here in DRAM row copy, in DRAM majority, Boolean operations, arithmetic operations, and what else can you do if you follow this programming model or this programming paradigm, right? So you can do other things like generating true random numbers by doing instead of doing triple row activation, you do 4 row activations, and you can do even better. These are keep building on better and better true random number of generators using the similar idea. So those are variations of that. You can also do physical unclonable functions puffs using multiple row activations, and also lookup table-based computation in case you want to do something like a transcendental function that is harder for you to approximate using arithmetic instructions. So someone asked about memory, other memory technologies. This is not limited to DRAM. So NAND flash memory devices can do also book bitwise operations by using a mechanism very similar to what I mentioned for triple row activation. So here is not triple row activations, is multiple word line sensing that enables you to do AND operations if your data is inside the same block, inside a plane, inside the die in an NAND flash chip, or across the OR is not here actually. Or if the data is across different blocks, you can do an OR operation. So you can also do AND OR, and then flash can already do not for inverted reads. So you can basically have a functionally complete model based on that. So that is for Flash. And again, we have results in the paper showing some performance benefits. Oh, I thought that I had for the NVA. So I didn't put the slide here, but this is not again limited for Flash. There are emerging memory technologies like PCM, ReRAM, which you can do constant time multiplication using a crossbar array based on Kirchhoff's law. Basically, what you do, you have these memories that use resistance to represent data. Then you put a matrix there inside the array, and then you put some voltage levels reference to the input vectors in the word lines, and then based on Kirchhoff's law, you end up having a dot product operation on the output. And there are companies as well, startup companies using that to accelerate neural network inference. There is a company in the US called Mythic. There's a very nice video on YouTube from this YouTube channel called Veritasium that they explain all of this very nicely. Highly recommend that video. And the YouTube channel is also very interesting. So, okay, all of this is very nice. But how you enable processing memory in current systems, right? For you to do that, you have to answer a bunch of questions, which is nice because then you can get a PhD out of it. And this is what I did. Like, for example, giving an application. Is my application going to benefit from processing memory? If my application benefits from processing memory, how can I program my application efficiently so that I can offload the computation to processing memory? Now that I offload the computation, how I need to handle things like data virtualization or virtual memory support, data alignment, data coherence, all of those problems. So all of these needs to be answered, and you need to create simulators, FPGA prototypes, so you can showcase the benefits of those systems. And all of this can be solved either by doing a PhD or with a mindset change from a processor-centric design to a more memory-centric design. And as I mentioned, it's very it can be exhaustive because you need to, for you to enable those systems, you need to touch many different aspects of the computer architecture stack, but you can do so step by step, one layer at a time. So in conclusion, this is one book chapter that summarizes a lot what I said here and expand on what I said here related to processing memory. It's very long, like 90 pages, like kind of like a book chapter itself. But if you are interested on learning more or understanding the current literature on processing e-memory, is a very nice starting point, especially if you want to do research on it. And I spend a lot of time writing it, so feel free to read. And if you find a typo, don't let me know. But yeah, it's a very nice introduction to all of those concepts that I mentioned over here. Just as a conclusion, the future for processing memory is very bright, which is very good news, especially for me, because I need to find a job. So if you also want to find a job after you graduate, processing memory is one thing that is very hot right now in the industry as well. And of course, in academia, if you want to do research on that. So there is a lot that still needed to be done for us to make better data-centric systems. And all of that would enable us to minimally move data inside ISOC, which can enable many things in the future, especially more energy efficient and sustainable architectures. So I guess this is a summary of what I just said. And I don't know if there's any question, otherwise I'm going to do a shameless marketing. Okay, if there is no other question, so we keep giving tutorials and lectures about processing memory. I just came back from Las Vegas where I did a tutorial on all of those subjects on processing memory that I just briefly mentioned over here. And we are having a next one in Asplos in the Netherlands. It's you don't need to go to the conference. There is also live stream online. You can just follow up on YouTube. And there is another one in the West in June, and then another one in Tokyo. I need to go to the West to talk in like 1 week. I don't know how I'm going to do that. And then for ISCA, which is another main conference for computer architecture. All of the tools that I mentioned here are available in our GitHub repository. You can play with them. And I guess that concludes the talk with time, surprisingly. If there is any question, I'll be glad to take. Otherwise, I hope it was intrusive or like you learn a little bit. At least you learn some of the papers that you might need to read during the semester. And then you can select all of the papers that I wrote and as a priority, because the slides are beautiful, as you saw. So you can reuse them. Okay, if there is no other question, that concludes the talk. Thank you very much for your attention, and thanks very much online.